Welcome. Let me remind you of what we were doing at the end of the last lecture. At the end of the last lecture, I had introduced the conformal time, which is defined through the expression given here. Conformal time is represented as eta, and d eta is dt, where t is the cosmic time, divided by the scale factor. And the line element, which allows us to calculate the interval between two events, can be written in terms of the conformal time in this way. We have a factor of the scale factor squared outside, which is a conformal factor, and inside we have c square d eta square minus dr square minus s square r into the line element due to the angular displacement. Now I had also pointed out that the conformal time provides, the main advantage of conformal time is that it provides a very convenient way to look at the propagation of light in space-time diagram. So we are used to a space-time diagram where we have c into the time ct over here and the displacement r over here. This is a space-time diagram where we have the comoving distance r along the x axis, and we have c into the conformal time eta along the y axis, and the propagation of light in this space-time diagram, the propagation of light is along 45-degree lines. If I had used the usual cosmic time and the comoving coordinate, the light would not propagate along 45-degree lines because of the factor of scale factor, because of the scale factor inside. But here the scale factor has been taken outside, and we know that light propagates along null intervals, so ds square is 0. So essentially d eta, if light is propagating in the radial direction, c d eta will be equal to dr. Okay, so the propagation of light is along 45-degree lines. That is the very useful aspect of this conformal time. So let us now use the conformal time and go back to the situation that we were discussing. The situation that we were discussing is as follows. There is an observer sitting here. These are the x, y, z. We are working in comoving coordinates. So these are x, y, z comoving, and there is a galaxy G, some comoving distance r away. And there is light being emitted by this galaxy which reaches this observer. That is the situation that we were considering. It is a very general situation, and here we are considering the situation where the observer is at present, but it need not be so. And we have already learned one aspect of this. We have learned that the radiation coming from this galaxy to this observer will get redshifted. The wavelength will increase, and we have calculated the redshift. The redshift we have seen is 1 plus z is equal to the ratio of the scale factor when the light is observed to the scale factor when the light is emitted. This is the ratio of the observed wavelength to the emitted wavelength. Okay. This is something that we have already calculated. Now an observer sitting here will not be able to measure the distance to the galaxy. The quantity that he will measure is the redshift. This is something I have already told you, that the redshift is the quantity that one directly can measure easily sitting on Earth. So an observer on Earth will essentially be able to measure the redshift of the galaxy. That is the quantity that is going to be measured. So the redshift in most situations is the quantity which is measured. For any astronomical sources, cosmological astronomical sources at a cosmological distance, the redshift is the quantity which is normally directly measured.
Sir, light which we are getting from that any distant object, how can we predict the how much is red shifted that way?
You cannot predict. You can, if you can identify some spectral line, this is something I have discussed. If you can identify some spectral line in the spectrum, in the radiation, then you know where the spectral line will be emitted if the object is at rest, and you know, so you know lambda emitted, and you now, if you can observe the wavelength where it is you are receiving it, you will know the redshift. Okay, so basically you have to do spectroscopy, you have to identify some spectral line in the radiation spectrum. Okay, so this depends on spectroscopy. Once you can identify some spectral line, you can then do spectroscopy and determine the redshift. This is the quantity that is measured. Let us now, okay, so let us now, before we go into anything else, let us first see what is the relation between the conformal time and the distance. That is for the propagation of light. What does it look like? So we shall come to this redshift, relation with the redshift later on. Let us first see what is the relation between the conformal time when the light is emitted. Let us say that the light is emitted when the conformal time is eta naught, eta emitted, it is received at a conformal time eta observed. It is quite straightforward that if you draw this in a space-time diagram, then the whole thing, set of events, will look like this. This is the observer, let us say c eta observed. This is the conformal time at the instant when the observation is done, which may be present. In most situations it will be the present, and if you look at the propagation of light that arrives here, it will have travelled along what is called the backward light cone. So light, if this is r, the trajectory of the photon that is reaching us will look like this in this diagram. It will come from the past. So these two events, light being emitted from here at eta emitted, light being observed here, the same photon being observed here at eta observed, will in the space-time diagram look like this. So this is c eta emitted, and this is the distance from which it is coming, the co-moving distance. So it is quite clear that the co-moving distance r is equal to c eta observed minus eta emitted. Okay, now the interesting and useful thing is to relate this to the redshift at which, so the redshift is what you can measure. Suppose there is a galaxy which I am observing at a redshift of 1, I would like to determine what is the co-moving distance, what is the value of the conformal time when it was emitted, what is the value of the conformal time present, I know. So these are things I would like to calculate. So that is what is of interest, how to determine these from the redshift. Okay, so let me discuss this. So the way you do this is as follows. We know that light propagates along a trajectory dr is equal to c d eta, and d eta we also know is dt by a, the scale factor. Now let us look at the definition of the Hubble parameter. Hubble parameter is defined as follows: dA by dt 1 by a is the Hubble parameter h at any epoch. That is how it is defined. So from this we can replace dt by dA divided by a into h. So this implies that dt is equal to dA a times the Hubble parameter. and we can put it in here. So what we have here is that this is equal to C dA by A HA. There will be A square here because there is 1 by A coming from here and there is already a 1 by A there. Okay. So you see, you can calculate, you can now integrate this, you can integrate this, and this integral will give us R is equal to C eta observed minus C eta emitted is equal to C, let me keep the factor of C, and I have to integrate this over the limits of the scale factor, the range being, the integral being dA prime by A prime square H A prime, and the limits are the value of the scale factor when the light was emitted and the value of the scale factor when the light is observed. Now we will assume that the observer is at present when the scale factor is 1, so A naught is 1, so A emitted is 1 by 1 plus Z. Okay, so the limits of this integral are 1 and 1 by 1 plus Z. Okay, so this expression is a very important expression. It allows us to calculate the difference in the conformal time between the light which we receive from a redshift Z and it being received, light being emitted from a redshift Z and reaching us now. You can in general use it to calculate the difference in conformal time between any two events. Here we are focusing on a particular event where light is being emitted at a redshift Z and reaching us now. It also gives us the co-moving distance corresponding to that source in terms of Z. How do you determine H of A? That we have already worked out from the dynamics of the expanding universe. You have to use this expression to determine H of A. So this is determined, H of A is determined by the dynamics of the universe. Okay, so you have to use this in this to determine the co-moving distance to any observed galaxy observed at a redshift Z. Okay. So let us now work out one particular case which is quite simple. Okay, one particular case which is quite simple. So the case that we are going to work out is where our universe is matter dominated. So we will assume that omega matter naught is 1. There is only matter in the universe, nothing else, dust, pressureless matter, like the galaxies that we have. Okay, so we will assume that there is only pressureless matter in the universe, there is no cosmological constant, curvature, whatever, etc., etc. So this is a very simple situation and it gives us considerable insight into what happens. So let us use this. So H square is H naught omega matter A to the power, omega matter is 1, so A to the power minus 3. So we will put that in here. Let us put that in here. So what we have then is, let me just write down the integral. Okay, so R is equal to C so we are going to put in the value of HA here, and HA in this particular model, let me write down HA first. So HA prime is equal to H naught H naught, omega matter is 1, omega matter naught is 1, and I have a to the power minus 3 by 2 because I have to take square root. Okay, so a prime to the power minus 3 by 2, that is what we have. This I have to plug in to the expression over here. So if I have a to the power minus 3 by 2, I have a square here, so I have a to the power half. So the integral that I have to do is essentially that this is equal to c by h naught. I have taken the h naught outside, sorry, I could have done it here itself, c by h naught divided by square root of a to the power half, right. That is the integral that we have to do. This will get multiplied with a square, so I will be left with square root of a prime, square root of a prime. And we know what this integral is, so this integral is going to be, there is no need for this, we can straight away put in the value. So what we have is r is equal to c eta naught minus eta emitted c by, this is equal to c by h naught. The integral over here is 2 square root of a, 2 root a prime, and the upper limit is 1, so I can put the 2 here. The upper limit is 1, so I have 1 minus the lower limit of a is 1 by 1 plus z, so 1 minus square root of 1 plus z. This is the relation which tells me the interval of conformal time, how that is related to the redshift of the source. It also tells me the comoving distance to the source in terms of the redshift. In a model where omega matter is equal to 1, purely matter dominated. Now the first thing that you should be wondering, we know that in the nearby universe Hubble's law holds. The Hubble's law is that the distance is proportional to redshift. So let us see if this is consistent with that. Is the distance in the nearby universe proportional to the redshift? Hubble worked in a regime where z is extremely small. This expression is valid everywhere for all values of z. Okay, so let us just look at this in the low redshift regime. In the low redshift regime, we can do a Taylor expansion of this. So if we consider z much less than 1, 1 plus z to the power minus half is approximately equal to 1 minus half z. So what we have here is that r is equal to 2c by h naught, 1 minus half z. So we are led to the relation that r is equal to c by h naught into z, which is Hubble's law. Okay, so we see that in the low redshift limit, it reproduces what we started off with. We started off the whole business from the Hubble's law, which was observed at low redshifts. Okay, but if you go to higher redshifts, you see the distance, the relation between distance, this is comoving distance, remember, and the redshift changes. So let us plot this now and try to see what happens at higher redshifts. So initially the graph between the comoving distance r and the redshift z is linear. As predicted by Hubble's law. But as you approach redshift unity, so this is when z is much less than 1. But now you see, as you approach unity, so let us look at large, as you approach unity there will be deviations from Hubble's law. The Taylor series will no longer be valid, And for very large z, let us see what happens at very large z. At very large z, the distance will reach a constant value which is 2c by h naught. 2c by h naught, that is the furthest distance, co-moving distance, from which a redshift of infinity corresponds to 2c by h naught. So this will look something like this. So it will reach a constant value which is 2c by h naught. Okay, so it will look something like this. It will saturate. You cannot have a value larger than that co-moving distance. Now this you see is very interesting, and as you go to higher and higher redshifts, according to Hubble's law, the distance should keep on increasing linearly. But here you have the fact that the co-moving distance, the furthest co-moving distance from which you can receive any radiation, which corresponds to redshift infinity, is a fixed value 2c by h naught. What is the interpretation of this? Well, the interpretation for this, to understand the interpretation of this, let us go back to our space-time diagram. So this is the observer. Observer is receiving light from this source, and the source in this space-time diagram is here. As the source is moved further and further back away, you are going further and further back in time. But you see there is the Big Bang which occurred. Let us say the Big Bang, we choose it so that it occurs at eta equal to 0. This is the Big Bang, eta equal to 0. So there can be no source which is, this is the Big Bang. This line, that is the event, that is the Big Bang. So at this value of eta, which is 0, we had the Big Bang. So eta emitted equal to 0 is the Big Bang, that is the origin. Okay, so the furthest distance that you can have a source, light started traveling, when light started, from which light could reach us, is this. If you can receive a radiation from this distance, that is the Big Bang. The scale factor is 0. If the scale factor here is 0, you see that the redshift A emitted is 0, the redshift is infinite. So redshift infinity essentially corresponds to the Big Bang, and this is the furthest distance, the distance that photon emitted at the Big Bang, which can travel till now, that is the distance 2c by h naught. This distance is called the horizon. So this distance is called the horizon. Okay, that is my horizon now. My horizon now in this cosmological model is 2c by h naught. A photon, so this is the furthest co-moving distance I can see. I am the observer over here. Photons emitted here, to reach me now, a photon should have been emitted here before, at the Big Bang. If a photon has to come from here to me, it should have been emitted before the Big Bang, which is not possible. So given the fact that the universe has been in existence for a finite time, there is only a finite distance which I can see up to, and that distance is the horizon. That corresponds to the Big Bang. Okay, I cannot see anything in principle earlier to that, because the universe was not in existence. The photon started traveling a finite time ago, a finite time period ago. Okay, and the co-moving distance it could cover in this cosmological model is 2c by h naught. There is no boundary, but this is my observable boundary. This is the boundary of my observable universe. The universe, not that the universe doesn't exist beyond that. If I wait one day, the distance I will be seeing is a little bigger. So it keeps on increasing slowly. okay, because the time that has elapsed since the Big Bang has increased. So I will be looking a little further. Okay, so this is the limit of the observable universe. Okay, I cannot at present see any part of the universe bigger than this. In the past that would have been smaller. Okay, now you see 1 by h naught defines a time scale called the Hubble time. So c by h naught is called the Hubble length scale, Hubble radius. This gives you an order of magnitude estimate of the distance from which furthest distance which you can see, and the value, exact value in this particular cosmological model that we have been considering. We have been considering a particular cosmological model, if you remember, and the particular cosmological model that we have been considering is omega matter equal to 1. In that particular model, the horizon is at a distance 2c by h naught. That is the furthest distance you can see. So that is the furthest region which is which can be causally connected to us through cause and effect. Anything beyond that is not causally connected to us in this model. It cannot be the cause for any effect now. Okay, because no signal can propagate faster than the speed of light. Now you should realize that the statements that we have made all depend on the cosmological model. So these, suppose I was in a different cosmological model, by that we mean if the density parameter had different set of values, then my Hubble h square a would be a different function and these results would be changed. Okay, so this entire relation, that exercise that we have worked out, is this relation is specific to a matter dominated universe. It will get modified, the relation between comoving distance and redshift, the difference in conformal time and redshift, everything will get modified if I change the constituents of the universe. Okay. Let me move on. Our interest here is in distances, and we have seen that in a cosmological model there is a furthest distance that we can see, and the way that distance from which the radiation is coming, the comoving distance, changes with redshift, has to be calculated using the formula which we have just derived, and we have worked out a particular example where omega matter is 1. Okay, but the comoving distance is not a distance which is of physical interest. After all, what does the comoving distance imply? It has, for most purposes, it has no direct physical implication. Okay, the actual distance at any instant of time, that's called the proper distance. So this is the actual physical distance. This is the quantity which is physical. If you had a meter stick, you would be actually measuring this, the proper distance. And the proper distance r proper is equal to the scale factor into the r co-moving, right. So if I call this r co-moving, then the proper distance is the scale factor into the comoving distance, and the scale factor is a function of time. So given a fixed comoving distance, the physical or proper distance keeps on changing with time. So obviously you cannot use light, the propagation of light, to measure the comoving distance. So if I asked you that, if I told you that this is the comoving distance to the particular observer here is whatever 100 megaparsecs, how would you determine the physical distance? You cannot send light from here to here because the universe expands as the light propagates. So one, in hypothetically what you could do, you could have observers all along who could simultaneously measure the distances using meter rules, meter sticks, and then finally you would have to add them up later on. But that is all just hypothetical. Okay, it's a thought exercise, you cannot really carry it out. So let us now move on to distances which are of physical importance, measurable quantities. So the first such thing is the angular diameter distance. Okay, so let me introduce this, the angular diameter distance. This is the distance, this is one of the distances which comes in important in observations. How is the angular diameter distance defined? The angular diameter distance is defined as follows. Suppose I have some object whose length is known, whose actual physical length is known. Let us say it is L. So its proper length is known, this is an object. Such an object is called a standard ruler. Whose we have reasons to believe that its length is kind of known. Okay, obviously, for example, let us take a galaxy. Suppose we have reason to believe that galaxies are of size 10 kiloparsec. I am just talking, giving you an example which is not realistic, but just to make the idea clear. Okay, suppose we have reason to believe that all galaxies have physical size 10 kiloparsec. Then I know that if I see a galaxy somewhere, I know that its size is 10 kiloparsec. Okay. Now we can define the angular diameter distance as follows. I am an observer sitting here. If I see the galaxy, it will then subtend an angle delta theta on the sky, and we know that okay, these angles are extremely small. So we know that the length L will be RA, the angular diameter distance, into delta theta. So if you know the size of the object of the galaxy, the physical size, the proper size, and if you can measure from Earth, if you can measure the angle it subtends on the sky, you can then determine the angular diameter distance to that object L by delta theta. So if you have some prior knowledge of what is the size of that object, suppose the object is what is called a standard ruler, we know its size is fixed irrespective of where you place it, and if you can measure the angle from the Earth from here, then you can determine the distance to that object, and that distance is called the angular diameter distance. Now here you see it is essential to distinguish between different distances. On Earth, in the standard Euclidean geometry which we deal with, these different definitions of distance all coincide, but in cosmology they will not coincide, as you shall see. So you have to be careful which distance you are talking about. So this is one definition of distance, it is called the angular diameter distance. Okay, now let us ask the question, suppose I see a galaxy at a redshift, some standard ruler at a redshift z, and I can measure so I know its proper size L, and I can measure the angle it subtends in the sky. So I know L, I know delta theta. Let us calculate the angular diameter distance as a function of z. What is the predicted angular diameter distance as a function of z? So to do that, let us go back to our line element. This is our line element. So you see the object is at a co-moving distance r, let us assume that the object is at a co-moving distance r and it subtends an angle delta theta. Okay. So, the length corresponding to that you can determine from here, the length corresponding to that L, what is the length? It is A into S into delta theta. You see, I have not yet talked about, let me just digress a little bit, I have not talked about the difference between R and S of R. There are two different functions over here. Here you have R, here you have S of R. In a spatially flat geometry, R and S of R are same, whereas in a curved space this becomes sine, if it is positively curved it becomes sine hyperbolic if it is negatively curved. Okay, what is the significance of this? Let me briefly just mention what is the significance of this. Suppose I have a radius of, I have a sphere of radius r, forget about the scale factor, I have a sphere of radius r, then the distance from the origin is r, co-moving distance from the origin is r. So this is my observer, this is a sphere of co-moving radius r. Okay, so this is the distance from of the sphere, from surface of the sphere from the observer, co-moving distance is r. Now let us ask the question, what is the co-moving surface area? To calculate the surface area you will not vary r, what you will integrate over is this angular part. You will do the solid angle integral, that will give you 4 pi, the solid angle part has not been changed. So the area of that sphere is going to be S square into 4 pi. So you see the, in this curved geometry the radius is r of a sphere, but the area is not 4 pi r square, it is 4 pi S square r. This is the main difference. Okay, because of the curvature, curved space, main effect of curved space, the ratio of the area of a sphere to the radius, square of the radius. So this ratio in flat space is a fixed number which is 4 pi, whereas in a curved space this ratio becomes S square r by r square, which is not 4 pi. Sorry, this 4 pi times this, okay, which is not the same as 4 pi. This ratio becomes dependent on r. That is the crucial difference. For small spheres, if you make the radius very small, how small should it be? If r is much less than the radius of curvature. If r is much less than the radius of curvature, so let me show you the thing that we had written yesterday, and everything should be much more clearer here. So the function S of r that occurs over here is r if it is spatially flat. This same function S of r that occurs over here is L sine r by L if it is positively curved. For small r, let us take the limit of small r. For small r, sine r by L is r by L, it goes over to r. So you see, on length scales much smaller than the curvature has no effect. It is just like the flat space. So if I consider a sphere which is very small, this ratio tends to 4 pi, it has no effect, the curvature has no effect. It is only on length scales comparable to the curvature that the curvature becomes important, which we know from our familiar experience on earth. If I look at a small part of the earth, I will not know that the earth is a sphere. Only if I travel large distances does the fact that the earth is a sphere become important. Same thing here. Okay, the ratio of the area of this surface of the sphere to the radius squared is different from 4 pi only if I go to length scales comparable to the curvature. Okay, so with this digression I have told you about the significance of this S of r. let us now go back to the problem that we were discussing. So for the problem that we were discussing, what happens is that for the problem that we were discussing, let me just write. So let me just 1 minute, let me locate the, or I can draw the picture again. So there is right. So there is an object here whose proper length is L, and it subtends an angle delta theta. So we know we want to calculate the angular diameter distance, which is defined as L by delta theta. Now L, the physical distance, the proper distance corresponding to an angular separation delta theta, is A S delta theta. So this L is A S of R, which I can write as S of Z, because I can calculate R if I know Z, and if I know R I can also calculate S. So I can write this as S of Z into delta theta, and the scale factor is the scale factor, value of the scale factor at the instant when the light was emitted, because this we have to evaluate we know that the delta theta into S into A is equal to the physical length of that object at the time when the light was emitted. Okay, so this should be A emitted. So all that you have to do is that you have to compare this with this, and you see that the angular diameter distance is equal to S Z divided into A emitted, and A emitted we know is 1 plus Z. Okay, so this is the angular diameter distance, how that changes with redshift. Let us now look at the cosmological model that we are discussing. We are discussing a spatially flat cosmological model. We are discussing a spatially flat cosmological model, and in this spatially flat cosmological model, R is related to redshift in this way, and in this spatially flat cosmological model, S of R is exactly equal to R. Okay, so let us in this model look at the behavior of the angular diameter distance as a function of redshift. So we would like to look at the behavior of the angular diameter distance as a function of redshift. So the angular diameter distance as a function of redshift in this particular model essentially follows R A Z is equal to R Z divided by 1 plus Z. Okay, that is the way the angular diameter distance behaves. So let me draw a picture of this. Let me draw a graph for this. Again you see for small z, the angular diameter distance is the same as the comoving distance, which we have seen follows the Hubble's law. So for small z it is going to be a linear behavior which is exactly the same as Hubble's law. Now let us look at what happens at large z. At large z, large values of z, this term vanishes from R, but the angular diameter distance is R by 1 plus z. At large z, 1 plus z is approximately z. So for very large z, the angular diameter distance is equal to 2c by h naught 1 by z. So you see initially it increases with a slope which is c by h naught, and for large z it falls with a slope which is 2c by h naught into 1 by z. So it falls off here as 1 by z, and in between it will have a peak value. So it will look something like this, the angular diameter distance as a function of redshift. Whereas the comoving distance to any object keeps on increasing with redshift and then it becomes constant. You see the angular diameter distance here has a very strange behavior. Why is this strange? Let us try to appreciate that. It is strange because of the following reason. From our familiar experience we know that if there is an object of a fixed size, and if you move further and further away from the object, it will subtend a progressively smaller angle. But in cosmology what happens is that if you have an object of a fixed size, if you place it at progressively further and further distances from you, the angle will decrease for till a certain redshift. After that the angle will increase again, because the angle which the object subtends is L by theta, delta theta, is R into delta theta. R will initially increase, see L is fixed, so angle is basically L by R. R is initially increasing, so theta is decreasing, delta theta, but after a certain redshift the R will again decrease. And finally if I have an object at the Big Bang, it will subtend, and what angle will an object at the Big Bang subtend? It will subtend 4 pi angle, it can never go to infinity, it will subtend, it basically fill the whole sky. Well, why is this happening? It is happening because the universe is actually, if I go to the past, the universe is smaller. So at the Big Bang, if you look at the Big Bang, all the light that reaches you from the Big Bang were emitted from the same point. So zero angle there will subtend fill the whole sky. Okay, so as you approach the Big Bang, the physical distance between 2 points from where the light was emitted will actually keep on decreasing. So if you look at a fixed solid angle, the corresponding physical distance keeps on decreasing if you look at a fixed angle. Okay, so it is this has to do, it's a combination of two things basically. Okay, one is that the distance increases with redshift, other is the fact that the universe itself, the scale factor itself is a decreasing function of time, redshift. Okay, combination of two factors which give rise to this behavior, the angular diameter distance. So let me remind you again, the angular diameter distance is important if you can measure the angle and the redshift and you know the size of the object. Okay, let me now introduce another kind of distance which is of relevance in cosmology. This is called the luminosity distance. So what is the luminosity distance? The luminosity distance is defined as follows. Suppose I have a bulb, 100-watt bulb, fixed luminosity, and I observe it from a distance. So this is my source, which has luminosity L, and I observe it from a distance r, from where I can measure the flux. So sitting here I cannot measure obviously the luminosity of the source. What I can measure is the flux F, which is the amount of energy that, so luminosity is the energy that is emitted per unit second, this is the energy that I receive per unit area per unit time, and we know that these two are related as 4 pi r square, this is equal to flux. So the r that occurs over here is the luminosity distance, it is called L, RL, there will be a subscript L. Okay, so essentially what here we do here is, if you know the luminosity, so there are certain objects, let us put a different sign here, okay, otherwise I will be confused with the length scale that we have introduced. There are certain objects whose luminosity is known, these are called standard candles. Like a 100-watt bulb. If I believe, if I have some prior information that my source is a 100-watt bulb, and if I can measure the flux, I can get the distance to the source. In cosmology there are astronomical sources for which we believe that the luminosity is known. Okay, we have reason to believe that we know the luminosity. So if you can measure the flux from such a source, you know the luminosity, you can measure the distance. Just like we have already talked about one such thing, that is the Cepheid variables. If you can measure the period, you know the luminosity. So Cepheid variables act like standard candles. Okay, and other thing which I should mention now is that we are here we shall work with the luminosity in a certain specific frequency range. So this is the luminosity in a frequency range delta nu. Okay, so let me I have to bring today's class to an end over here because we have run out of time. So I shall do the calculation of this luminosity distance in the next class. Let me briefly recapitulate what we have learned in today's class. In today's class we first learned about the conformal time, and we saw that it is a very useful thing to look at the propagation of light, and we learned then how to calculate the co-moving distance to a source and the conformal time when the light, to calculate the conformal time when the light was emitted from the source in terms of the redshift, the measured redshift. We learned how to do this, and we saw that this relation, we saw that there is a furthest distance to which you can see. So if you have a source which has a redshift infinity, that is the furthest co-moving, the furthest redshift that you can have, and there is a finite co-moving distance corresponding to redshift infinity. This we learned, I told you, is the horizon. So that is the furthest distance a photon emitted at the Big Bang can propagate. Okay. Next I told you about the proper distance, which is the actual physical distance between two objects. Unfortunately we cannot measure it directly. Finally we moved on to things which are of physical significance in measurements. The first thing that we talked about was the angular diameter distance, and we saw that the angular diameter distance is the relation between the angular size of the object and the proper size of the object. So it relates the angular diameter, measured angle subtended by that object to the proper size of that object. And then finally we started discussing the luminosity distance, which relates the luminosity to the flux. So let me end today's lecture here. We shall continue with the luminosity distance in the next class.